Welcome to This Explainer. Today, we've got an absolutely awesome goal. We are going to completely demystify exactly how 3D graphics are built directly into a standard web browser. If you've ever played around with one of those sleek 3D product showcases or a browser-based game and thought, wow, how do they actually pull this off? Well, you are in exactly the right place. It all really boils down to one fascinating question, doesn't it? How in the world do you take a bunch of abstract mathematical coordinates just floating out there in a void and transform them into a living, breathing 3D space on your perfectly flat 2D screen? I mean, it totally feels like magic, but honestly, it's just a brilliant combination of math and rendering pipelines. Okay, let's dive into this. So, if you want 3D in a browser, the underlying engine making it happen is WebGL. But here is the painful reality about native WebGL. It is a highly complex, very low-level system. Straight out of the box, WebGL really only understands how to draw points, lines, and triangles. That's it. If you want to build a full scene, you are looking at writing a massive mountain of heavy, math-intensive code just to get a basic shape on the screen. Enter our hero, Three.js. This JavaScript library essentially wraps all that painful WebGL math into one incredibly intuitive package. It handles the scenes, the lighting, the shadows, and all the 3D math easily, so you literally don't have to write it from scratch. So here is our roadmap for the explainer today. First, WebGL versus Three.js. Then, setting the 3D stage. Next, building the Hello Cube. After that, lights and animation. And finally, modern tools and setup. Let's get to it. Part 2. Setting the 3D stage, where we define our core space. You know, using Three.js is kind of like directing a movie on a digital stage. And at the very heart of this is something called the scene graph. Imagine the scene graph as your movie studio. It's basically a tree-like hierarchical structure. Every single object you create, your lights, your cameras, your 3D models, they all get placed into this tree in a parent-child relationship. Why does this matter? Well, because children are always positioned and oriented relative to their parent. So think about building a 3D car. If you make the wheels children of the car object, moving the car automatically moves the wheels along with it. It's an absolute lifesaver for keeping your 3D world perfectly organized. Now, to actually capture this stage, there are 3 absolute essentials you need. First up, the scene. This is the root of your scene graph. It's the actual stage itself. Second, you need a camera, specifically a perspective camera, which acts as your literal lens into this world. And third, the renderer. Think of the renderer as your director. You basically hand the scene and the camera over to the renderer, and it crunches all the numbers to draw that final 2D image right onto the HTML canvas element on your webpage. Now, what's really interesting about this is how the renderer actually decides what to draw. It relies on a concept called the frustum. Imagine a 3D shape that looks like a pyramid, but with the very top tip entirely sliced off. That's your frustum. When you set up your camera, you're giving it a field of view, an aspect ratio, and near and far clipping planes. Those 4 settings together carve out this exact shape. Anything inside that invisible frustum box, it gets drawn to your screen. But anything outside of it, or stuff that's way too close or way too far away, gets clipped and completely ignored by the renderer. It's a brilliant way to save on processing power. All right, moving to part 3, building the Hello Cube. Let's add our very first object. So in the world of 3D programming, objects are called meshes. And a mesh is really just a simple 3-ingredient recipe. Ingredient number 1 is the geometry. This holds the vertex data, the literal physical shape of the object, like a box or a sphere. Ingredient 2 is the material. Think of this as the object's costume. It defines its color, how shiny it is, or maybe what image is wrapped around it. And finally, ingredient 3 is position and orientation, basically exactly where it stands on the stage relative to its parent. Mix those 3 together, drop the mesh into your scene, and boom, you have a 3D object. But here's the catch. If you go follow that exact recipe right now, create a basic box geometry and render it, you're probably going to be a little disappointed. You'll look at your screen and think, wait, why does our 3D cube look like a completely flat 2D square? Well, it's because if your camera is looking directly down the z-axis at a perfectly static, unlit box, you are only seeing one single flat face. Without any depth cues, 3D just looks, well, flat. Which brings us to part 4, lights and animation. Time to actually bring these scenes to life. Okay, so to prove to our brains that this cube isn't just a flat square, we absolutely need some motion. To do this, we set up a render loop using a built-in browser function called requestAnimationFrame. Basically, this is just a polite request telling the browser, hey, I want to animate something, please draw this scene over and over again, ideally around 60 times a second.
Inside this loop, we take the time that's passed, usually converting it from milliseconds to seconds just to make the math easier, and we continuously update our cube's x and y rotation. And just like that, our square starts spinning, and we can finally see that it actually has sides. But actually, this brilliantly illustrates our next problem. Even while it's spinning, our cube still kind of looks like a flat, solid-colored block. Why? Because we initially used a mesh basic material. Basic materials literally couldn't care less about light. They just render a flat color. So to fix this, we need an outfit change. We swap it out for a mesh Fung material. The specific material actually calculates how light hits its surface, creating real highlights and real shadows. And that is exactly the visual cue our brains need to perceive true 3D depth. Of course, a material that reacts to light needs, well, an actual light source, right? So we bring a directional light into our scene. If we position this light slightly to the left, maybe a bit above, and behind our camera, and then target it straight at the center of the stage, something magical happens. The light strikes the spinning cube perfectly. The faces dynamically catch the light as they turn, the edges suddenly pop out, and there you have it, an undeniable, beautifully shaded 3D spinning cube right there inside your browser. Now, here is a really fantastic efficiency tip that totally highlights the power of Three.js. Let's say you decide you want 3 cubes on your stage. You do not need to create the shape data 3 separate times. No way. You can use literally one single box geometry. From there, you just create 3 unique materials, like say a red one, a green one, and a blue one. Then you combine them into 3 distinct meshes and space them out along the x-axis. One single shape, but 3 different actors. The scene graph architecture makes this kind of memory reuse incredibly simple and performant. And that brings us to part 5, modern tools and setup, or how to actually load Three.js properly today. So, practical question. How do you actually get Three.js into your web project right now? Well, web development moves pretty fast, right? As of Three.js version R147, the modern, standard way to load the library is by using ES6 modules. You just use a standard script tag with type set to module. But, and this is absolutely crucial, if you just type import star as 3 from 3, your browser is going to throw an error. Why? Because it has no idea where 3 actually lives. This is what developers call a naked specifier. To fix this, you absolutely must use an import map in your HTML. Think of the import map as a directory. It tells the browser the exact file path that the word 3 refers to. Plus, it makes importing cool extra add-ons like camera controls super clean and totally painless. And just like that, you now understand the core mechanics of 3D web graphics. We went all the way from the pretty daunting, math-heavy world of raw WebGL to easily spinning beautifully illuminated cubes on a structured digital stage using Three.js. It really just goes to show how incredibly accessible this technology has become for everyone. So I'll leave you with this thought. Now that you hold the recipe, the scene, the camera, the geometry, and the light, what kind of interactive 3D world are you going to build next? Thanks so much for joining me in this explainer, and I'll catch you in the next one.